Okay, time to get started. Quick reminder as usual, at least temporarily as usual for the moment. Don't forget about the attendance quiz, attendance code. Here it is. Don't forget it disappears in a minute and a half at this point. So make sure to get that done. Okay, picking up where we left off last time. We're still in section 2.1. We finished earlier discussions and are moving on now to rotations. Now, I think this is a really important idea. We're going to start considering the question of when you have an equation of three variables, what does the resulting surface look like? And bad news, good news. The bad news is we're not going to be able to answer that question in general. It's a really, really, really hard problem in general. Right? The good news is that is not our goal. Our goal is going to be to understand certain techniques that will allow us to answer the question for a pretty large and commonly experienced set of cases, and that's just going to be good enough. Okay. All right. So the first point is this trick about rotations. I think this is an underappreciated idea. This isn't emphasized in most textbooks that I've seen anyway on the subject. Here's the big point. If, now that's a big if. This will not always be the case. This will usually not be the case. But if x and y appear in the equation only as part of this expression, square root of x squared plus y squared. I mean, there's plenty of examples. We'll see some examples that follow where there just aren't any x's and y's in the equation other than as part of that expression. Then we get an awesome conclusion. Then that surface is rotationally symmetric, specifically around the z-axis. I love this result because it's a low-cost, high-payoff type result. It is very easy. At a glance, just look at your equation and look at where the x's and y's are. And see, is this green condition true or not? It is eyeball glance, easy to do. Doesn't cost you hardly anything, right? And then it has this high payoff that we get this powerful geometric conclusion about our surface. Rotational symmetry around an axis is a tremendous amount of information, right? So low cost, high yield, awesome. Now, why is this true? Here's my take, anyway, on why this is true. I'm going to give you 2 points of view on why it's true. Let's consider these 2 points here. We got that point, and we got that point. Now, those are different points, of course. As you can see, I've arranged it to where one is a rotation of the other, and vice versa. They're different points. They have different x and y coordinates. When you plug the x, y, and z coordinates into the equation, you're plugging in different numbers. So it's not immediately obvious that everything's going to work out. But here's the thing. The x and the y, while they are different x and y, but the x and y are what allow us to compute these two distances. And since these are rotations of each other, those distances are computed by the same expression, square root of x squared plus y squared. And if that's the only way that x and y show up in the equation, we don't really care that x and y are different. X and y are just things that produce square root of x squared plus y squared, which are the same for these 2 points. So as far as maybe not the immediate arithmetic of the equation, but the eventual, once you plug into that expression square root of x squared plus y squared, the eventual arithmetic of the equation involves the same, square root of x squared plus y squared, the same z. So we're effectively doing the same arithmetic for both points. And so either they both work or neither works. Right? And so with that in mind, if you think about it, what that means is when you have any point on your surface, everything that you rotate that point to produce also on the surface. And that's why we get the rotational symmetry. One point of view, anyway, on why we get the rotational symmetry. Okay. All right. Now, here's another point of view, and this is pros and cons, arguably a little quicker, but different points of view. Let's think about what it would mean. What can we conclude from this condition here? Again, suppose x and y appear only as part of that square root. If I were to convert this equation into cylindrical coordinates, there wouldn't be any thetas. I mean, square root of x squared plus y squared is going to translate as absolute value of r. Where else does theta come from? Right? X's and y's are all part of that turn into r, and then z is already z. There's no thetas in the equation. We've already talked about this as a neat punchline. Whenever you have a cylindrical equation with no thetas, we've already talked about how that's rotationally symmetric around the z-axis. So, different point of view, arguably a little quicker, kind of piggybacks off an old idea we've already discussed, but anyway, two different points of view. Okay, how is this useful to us? I ask rhetorically. Here's the thing. If you have a symmetric surface, rotationally symmetric surface, now this is a geometric appeal. I'm just, hoping that your intuition will be satisfied by the following. If you have a rotationally symmetric surface, you can look at the cross-section in any plane containing that z-axis and just rotate it around. Right, so let me do a hand wave. If our surface really is rotationally symmetric, any cross-section, the process of rotating that around will produce all the other cross-sections, and therefore the whole surface. Does that satisfy? So this is a massively powerful tool, and let me just show you a quick example of how this is so convenient. Actually, let me zoom in a little more. There we go. So let's go back to this question. We talked about this surface last time, and I made an apologetic reference to, I'll show you later how we're going to figure out what this surface looks like. I just asserted that it was a bowl of sorts. So here's my process. First, check it out. X and Y appear only in the required form. Now you may quibble. You are right. Technically, there is no square root written in there. But keep in mind, what I've written there is equivalent to z equals square root of x squared plus y squared squared. So, same exact surface because they're totally equivalent equations. And this strictly satisfies the condition. X and y appear only as part of the special form. Is everybody cool with that little side step, a little slick move there? Okay. All right. Okay, so that noted, since it's rotationally symmetric around the z-axis, because of this form, I can then say, as we just observed, pick any plane, suit yourself, any plane that contains that axis. Now I'm picking the YZ plane here, whatever, it doesn't matter. If you want to pick the, see if I can draw, if you want to take the XZ plane, or if you want to take some other plane, any plane that contains the Z-axis, whatever. Got to pick one, and just to get the ball rolling, I'm going to pick the YZ plane. If I can understand the cross-section in that, if I can understand the cross-section of the surface in that plane, all I got to do is rotate that cross-section. And that cross-section is really easy to understand. We're looking in the plane, x equals 0. That's what this plane is. I can plug that in, and what comes out when I do that plug in, this just turns into that, which is straight up, very familiar, just a parabola that looks like that. And it's all over the shadow at this point, right? So we've already observed that our actual surface is rotationally symmetric. We know that if I look at any cross-section containing the axis, of course, right, that I can just rotate it around the z-axis. Here is that cross-section, easy algebra. And rotating this purple parabola, not a hard challenge, right? Rotating that purple parabola is clearly going to make a kind of a ball shape. Anybody see how I did that? So it's a really powerful idea. Oh my gosh. By the way, side note, this surface is called a paraboloid. A little unsurprising, I think. It's based obviously on the fact that it's a rotation of a parabola. So anyway, heads up on the term paraboloid. We'll be using that term here and there. Okay. All right. So that's the thing. That's the deal. That's why this observation about rotational symmetry is so powerful. It allows us a foot in the door to identify surfaces. Let's see another example. Here's one. Ooh, weird. What is that thing? Well, again, x and y in the proper form. This is rotationally symmetric around the z-axis. Again, pick your favorite plane containing the z-axis. Doesn't matter. Last time I picked the yz plane. Just to show I can, this time I'm going to use the xz plane, otherwise known as y equals 0. Doesn't matter. Any plane you like. Suit yourself. Good general rule of thumb. Usually it's easiest to pick a coordinate plane. I don't recall ever seeing any instance where there's any advantage to not picking a coordinate plane. So there we go. Let's pick y equals 0. How am I going to understand what this cross section here looks like? Well, that cross section, again, that's what happens when I look in y equals 0. And that makes this equation turn into this equation. And now flashbacks to high school. Y'all remember your what they used to call Algebra 2 when I was in high school. I don't know what they call it these days. It's probably different in every school. But anyway, at some point you learned about hyperbolas, right? And by the way, make sure that you're good to go with how to draw hyperbolas. There's always this question of, wait, is it like this or is it like that? Which way does it open up, right? You gotta get that straight. How you get that straight is up to you. If you don't have a confident means of keeping that straight, come talk to me in office hours. I'll be happy to show you my little personal favorite trick on that. That's how I remember it. Again, we can talk in office hours. But that's that hyperbola that I've got drawn. And now again, geometric appeal. I've got my cross section. I know all I have to do is rotate it around the z-axis. And so geometric appeal, rotating that hyperbola, makes this shape, something kind of like that. And there you go. So that's what that surface is. Everybody good? It's a pretty cool method. By the way, this is called a hyperboloid. Again, no surprise. It's a rotation of a hyperbola. This one's called a hyperboloid of one sheet. We'll see why momentarily. Okay, moving along. Let's do another one. Now, this next one is a bit different. I'm going to make the assertion that there are... Oh, yeah, go ahead.
I have a quick question. So, in the previous equation, if we wanted to, turn it into cylindrical, we just have to substitute x squared plus y squared.
Yep, that's right. Absolutely. And then you can effectively make a similar argument. Yeah, absolutely. Right. So, and that's a perfectly fine way to do it. The problem with that point of view is that point of view with cylindrical coordinates can't do the little trick that I'm about to pull in the next example. But it's a perfectly reasonable way to go. Sure. Okay, so when x and y appear in the proper form, keeping in mind how our argument went there, the whole point is that this proper form, what I'm calling this proper form of x and y, it represents a distance, and when you rotate, that distance is preserved. That's really kind of the point, right? So let's suppose I were to just take this same idea, and instead of x and y, maybe it's x and z. If x and z appear in the special form, now you're talking about distance to the y-axis. And if y and z appear in the special form, we're talking about distance to the x-axis. So there are two analogous theorems, and I think it would be a lovely exercise to think through this picture. How would this picture change if you're making a rotational symmetry argument about the x-axis instead of the z-axis? How would it change if you're arguing around the y-axis? Right? Think it through, draw the picture, persuade yourself of how those theorems work. And here's how we're going to use one of those theorems. So this algebra here, this example, x and y, no luck. Right? It just doesn't work. X and y do not. I can't rewrite it so that x and y appear in the proper form. We lose. This thing is not rotationally symmetric around the z-axis. But if I rewrite it like so, you notice that y and z do appear only in the special form. And so this is rotationally symmetric around the x-axis. And we're going to proceed in a basically analogous way. We've got a different rotational symmetry now. And we're going to play the same sort of a game. If it's rotationally symmetric, I can pick any plane containing the axis. Again, you got options. I'm going to pick the xy plane. Doesn't matter. If I'd wanted to pick the xz plane, that would have been fine too, but whatever, I'm going to do the xy plane, which is described by that equation, which I can plug in to see what the intersection is. The intersection is that. Again, hyperbolas, again, flashbacks to high school algebra. Make sure you can get it straight. Make sure it goes the correct way. Easy to mess it up. But that is a hyperbola that looks like this, approximately. And now, again, geometric appeal. I know the cross section. I know it's rotationally symmetric around the x-axis. Rotating that purple hyperbola produces, oh gosh, and it's so hard to draw this one, but it's like I get these two. I like this. I don't know why. This is silly, but to me, this looks like a couple of contact lenses. You know what I mean? I like to call this the staring contest. Anyway, different surface. Still a rotation of a hyperbola. Still a hyperboloid. But you see, this one has kind of two disconnected chunks, you might call them. We call this a hyperboloid of two sheets to distinguish it from up here, hyperboloid of one sheet. Yeah, question? Oh, okay. Yeah, cool. Sorry, I just wanted to finish that thought. Yeah. Yes.
So what exactly is a sheet?
That's just a term. It's just a reference to the fact that this is all in one connected chunk. That's all. Yeah, and this, it has two disconnected chunks. And we can make that formal, but that's not what this class is about. Yeah. But you see what I'm saying? Like this piece and that piece, they don't touch, even though they're part of the solutions to the same equation. Yeah.
So I could remember it as the number of chunks.
Yep.
The number of sheets.
Yep.
Okay.
Yep. Absolutely. That's all they mean by sheet. They just mean chunk. Yeah. Yes.
Actually, quick question.
Yeah.
Let's if I were to work in the reverse. And
Yeah. Great. Yep.
In cases where it's rotationally symmetric, that means I don't need to define anything for my angles, right?
I'll tell you what. Let's actually walk through one. So let's reverse this one. So what we did when I presented this previously is I took this equation and I argued that this is what is produced. Now we're going to turn that around. We're going to assume that we have this surface, which, by the way, we're going to assume that means that it's a rotation of that curve around the z-axis. Right? So assuming that all I know about my surface is that it's a rotation of this parabola in this plane around that axis, how do I know what I have? Okay, well, here's the reverse argument. That equation is clearly this. And let's see here. I'm in the plane x equals 0, which again, presumably I know. And because of this rotation, I know that the equation, the equation needs to involve the expression x squared plus y squared. That can be the only way that x's and y's are allowed to show up. But when I plug in x equals 0, right, I'm trying to reverse engineer, what expression involving only square root of x squared plus y squared, when I plug in x equals 0, will turn into this. And you sort of realize, oh, well, the y squared, I'm going to need that to be x squared plus y squared. And that x squared will go away as required, and it's kind of work out. So yeah, it's just you just kind of have to, speculate on what would be the reverse of that process. Is that satisfying?
Yeah, but
okay.
I mean, let's say, because in the textbook they had questions where, they define, they start off by defining, certain ranges. So they say, z is bounded by 3 and 0 for, a sphere of radius 3 or something like that. In such a case, if I were to derive an equation for this, I would not have to derive an equation for the angles, right? Because we know, I wouldn't have to say it's bounded by 0 to pi or how many rotations.
That's just not what we're doing here. I mean, it's kind of a different category of question. Okay. I remember the exercises you're talking about. Right now I just want to talk about how to understand equations.
Okay.
Is that cool?
Yeah.
Okay. Yeah. Right. Okay. All right. So that's how rotations work. Oh, by the way, there's a million other examples that y'all can produce for yourselves. Or, of course, another thing that y'all can do on this is y'all can look back at my old exams, which I'll remind you, all posted online. There's a lot of them. Right, don't forget, it's not just Math219. Right? Math212 is practically the same course. It's a little different, but it's not much, right? And so if you look at, there's 3 different folders that are linked on the course resources webpage. 3 folders of old exams and solutions. And if you go through those, you will find tons of questions that are kind of in this general area. So take a look at those, and what you're going to find is that it's kind of always the same, morally the same process. All right, moving along. Okay, so deformations. Now this is another tool for understanding what do equations look like. And again, we're looking at 3 dimensions. We got equations involving, let's say, x, y, and z. I don't know what this equation describes. It's some sort of a surface, but what surface is it? How do we figure out what surface it is? And this idea of deformations is that if you already know the answer to one such question, you can tweak it to get the answer to a different question. So for example, this right here, I'm going to call that an easy one. This says distance to the origin is 13. So that's pretty obviously a sphere of radius 13, right? So I know what the set of solutions to that equation is. We got lucky, right? You won't always get that lucky, obviously. Okay, so that one I understand. Question, if I were to take this equation, and if everywhere I see a z, I were to replace, just kind of, copy paste, right? Just erase where it says z, and wherever z was, replace that with 2z. What happened? Right now, this is, keep in mind, this is not, doing algebra, right? This is not a reversible, this is not the same, the new thing is not the same as the old thing. I'm definitely getting a different surface here, right? So the question is, in what way will this surface be different? Now, I like to think this through in the following sense. I like to think through that, okay, if I look at, here's a point, right, this point here, 3, 4, 12, satisfies that equation, easy arithmetic. By the way, that's an example of what's called a Pythagorean quadruple, kind of like a Pythagorean triple, a little bit different. So that particular point plugs in, that equation works. Would that point work in here? No, obviously not. Right? Look at the z. The z is 12. If I plug in the 12 here, where the z used to be, Now that z gets multiplied by 2. Now I'm looking at 24 squared crash and burn. The arithmetic just doesn't work. Of course it doesn't work. It's a different equation. But we can get clever with it and point out that, well, yeah, it is a different equation, but if I were to look at the point 3, 4, 6, then that 6 goes in where the z goes, and it gets multiplied by 2 and becomes the 12 that already made the arithmetic work. Okay, so we're kind of anticipating, this multiplication by 2 right here is kind of what screwed it up before. If I divide by 2 in anticipation of having to multiply by 2, we cancel out the screw up. Everybody see what I mean? So that works. And then I have actually a pretty good answer then to my original question, which is what's the effect? What is the effect of everywhere I see a z, I put a 2z? What that effectively does is it takes all the z coordinates and it divides them by 2. It's like I'm squishing. Geometrically, I'm squishing in the z direction. All right, so this is a category of tools that mathematicians like, is being able to make connections between algebra and geometry. Right, so the takeaway here is that this algebraic tweak causes this geometric consequence. That's what I call it, deformation. Okay, so this is a pretty generalizable thing. In some sense, whatever you do in the equation, sort of the opposite happens to the surface. Again, in anticipation of whatever it was that you did in the equation. And so you can apply this in a lot of different ways. Here's another example. How would I figure out what this looks like? That's not rotationally symmetric. It's not a statement about distances. I don't have any, it's not clear how we're going to get our hands on that thing. But this, we've already agreed, we understand that, again, just a distance argument. Just give me a second. Yeah. So that one I already understand. That's an easy freebie. I can notice that all I'm really doing is, for example, everywhere I see an x, I'm replacing it with x over a, like so. And so how would I sort of anticipate and cancel out the effect of dividing x by a? Well, all those x coordinates just need to get multiplied by a. And so that little substitution just stretches by a factor of a in the x direction. And then likewise in the y direction, likewise in the z direction. And we therefore have a stretched out sphere. Right, in green is an actual sphere. And these three substitutions just stretch it out to make a, again, hopefully no surprise, we call this an ellipsoid. Sorry, you had a question. Yeah.
So, why are we saying that ellipsoids are not rotationally symmetric?
Well, they're not.
Aren't they, like, along...
Maybe. I mean, if A, B, or C, if any two of A, B, and C are equal to each other, but in general, if they're not, right, if A, B, and C are all, like if A is 2 and B is 5 and C is 17, that's just a weird shaped, it doesn't have any rotational symmetries. Now you might get lucky if A and C happen to be equal, then and you can make a rotation argument. But not in general, right? And again, easily detected, because if it did have that symmetry, then we would have to algebraically be able to identify x and y as being only in the proper form, and they just aren't. Yeah. Good question. Okay. A few other examples. This is pretty readable. I'm going to let you all read these, and likewise there's some other examples in the book. So take some time, give a look to those. Notice, one thing I do want to point out, you just got to be really careful with the following. What is the process? What is the deformation? What's the little algebraic replacement happening here? And it's tempting to say we're replacing x with x over a squared, and that's wrong. So you got to keep in mind, wherever the x is, right, that's where you have to replace. So imagine that there's sort of parentheses like that. And what would I put in the parentheses there instead of x to make this turn into this? And you can see whatever I put where x is going to get squared. So the replacement here is that x is replaced with x over a. Everybody good with that? So it's a little landmine you got to be on the lookout for. So be careful with the algebra, and little stuff like that can unexpectedly sting you if you're not careful. Okay, moving along. So we are done with section 2.1 now. Moving on to 2.3. Oh, hey, wait a second. What happened to 2.2? 2.2 is about limits, and it is important math. It's beautiful math. It's sophisticated and kind of proofy, and not really what this course is about. So it's a section that we used to include limits in multivariable calculus courses like 219 and 12. We sort of got rid of it in 212 before we created 219. But back in 212, long ago, it was part of the course. It was one of my favorite parts of the course. It was one of the students' least favorite parts of the course. And so we've kind of slowly taken it out. Now, anyway, if you want to read that stuff, you're welcome. You're not required. It's not part of the course. But mathematically, it's actually really cool. Okay, so we're going to talk about derivatives. This is a weird statement right here. There's more than one kind of derivative, and I don't mean with respect to different variables. I mean there are qualitatively, fundamentally different, importantly different constructions, all of which are kind of in some way or another derivatives. When you're doing multivariable calculus, this is not true in single variable. In single variable, there's the derivative, end of story. I guess there's second derivatives, but that's not what we're talking about, right? So I'm talking about still among first derivatives. There's several. So that brings up some weird questions. One thing is, y'all recall I gave you this warning about how when you look at a picture in multivariable, you can't just go around assuming every picture is a graph, because they aren't. There are some kinds of pictures that are produced in totally different ways, and you can't interpret them as if they were produced in the graph way. Right? Not every picture you draw is a graph. Some are level sets. Some are parametrized curves or surfaces. So, in the same way, you can't just say, we got all these different kinds of derivatives that we're about to see. I'm going to just kind of treat all of them like they're slope of the tangent line. Not even close, right? Totally not. We're going to see various different kinds of derivatives that all have different geometric interpretations. And so in your minds, you've really got to partition, in your head have sort of one kind of intuition that you develop for what are this kind of derivative and how do I interpret that geometrically, and then have a totally separated partition in your mind of, hey, here's a different kind of derivative. How do I think about those geometrically? And then likewise for the others. Okay. They all have a common feature, though. In their different ways, they all relate input changes to output changes. I think this is a really great way to think about what they all have in common. Why do we call different constructions by the same name derivative if they're different? It's because of this unifying feature. They all, in their different ways, they relate input changes to output changes. Is that cool? Everybody on board so far? Okay. All right. I'm going to start with partial derivatives. The book starts with partial derivatives. Most books start with partial derivatives. I don't think that's a good choice, honestly. I think there's some big downsides to starting with partial derivatives. But I feel like my hands are a little bit tied here. The book starts with partial derivatives, so I'd either have to digress very substantially from what the book does, which I've tried before in the past, and I think it creates more problems than it solves. Or I can just, sigh and accept that I'm going to have to do it the book's way. So that said, the argument in favor, partial derivatives are super easy to compute. That's pretty sweet. It's very satisfying. It gives you that sense of, oh, I got it. You get that mental reward of, oh, I did one, right? Very easily, we're going to do so on the next page. It's super easy to compute. And it's going to be familiar in a lot of ways. And that's kind of nice, right? To be able to, as we go into multivariable calculus, have our first step be something that rings a bell. Satisfying in that way. Okay, the danger, and the reason that I personally, if it was up to me, I wouldn't do it this way. Ultimately, the best derivative, the most important idea for y'all to retain about multivariable derivatives is not this. And I fear that by starting with it, y'all might sort of take this subtext of, okay, I guess this is how I should be thinking about things. And I don't think you should in this case, right? So do not hang your hat on this point of view on differentiation. Think of this as this is ultimately going to be a disappointing, highly limited, narrow first attempt. I don't want to say it fails. It doesn't really fail. But we're going to do much better than this. And that much better thing that we're going to see later today, I don't know, maybe later today, probably tomorrow, much more valuable, much more useful, and that's where you should hang your hat. Okay, all of the warnings said. Here's how you compute partial derivatives. There's actually not much to it. You got a multivariable function. So, for example, you've got z equals f of x1, x2, ... through xi, ... through xn. Let's say, all right. What we're going to do is we're going to pick one of the variables, one of the input variables, to stay a variable. And we're going to hold all of the other variables, constant. So that's going to stay constant, that's going to stay constant. Now that's an aggressive move, right? Somebody comes to me with a multivariable function with a bunch of input variables and says, we're going to play make-believe and pretend that all these variables are constants, except for that. Right? Aggressive move. Okay. That said, I now have one output variable that is, in fact, a function of, one input variable. I now have a single variable function as a result. If you have a bunch, it's one of these kind of tree falls in the woods kind of thing. If I have a bunch of variables but they're not allowed to change, are they variables anymore? They're really not variables anymore. They're just constants, right? So this is a single variable function in effect. And so the idea of a partial derivative is that we just take the regular good old Calc 1 derivative of that resulting single variable function. That's all it is. That's all a partial derivative is make believe that all the other variables are constant and take your good old, regular old, plain old, familiar derivatives. Okay. Before we get into a computational example, let me describe the notation for this. So this is one of the notations. You can again, kind of like in single variable, you can view this as being kind of a separate thing that you then apply to f, thus giving you this other notation. You've probably seen things like that in single variable calculus. There is kind of a, y'all remember the f prime notation for talking about derivatives? This is kind of analogous to that. Of course, you can't say prime. Prime wouldn't tell you which of the several variables you're continuing to view as a variable. So, but kind of avoiding the whole faux fraction sort of thing, kind of like f prime, making the variable a subscript. Another optional notation for how to write this. Okay, and then a real quick warning. This symbol here, that symbol is not a D. I know it looks kind of like a D. It's not a D. Very importantly, not a D. D means something different. D is not an alternative optional notation. It just is wrong, right? So don't make the mistake of writing a D here. And now, again, we find ourselves in this tedious situation of having to write down tons of times a new symbol that you probably haven't ever written before. I wouldn't be surprised. Maybe you have. But most of you have never written this before, and it's silly and a little bit borderline humiliating, but I think it's necessary to just, kill a couple of minutes by sitting there and practicing how to make that symbol, and so you don't reflexively fall into the unacceptable habit of writing a D. By the way, it's also not the lowercase Greek letter delta. Also unacceptable. Can't do it. Okay, let's do one. Here we go. How would I take this monster, and how would I take its partial derivative with respect to y? Now let's just take a moment to recognize how scary this looks. Right? It's a product of three factors. Oh my gosh, we're going to probably have to use the product rule. Oh my gosh, look at this factor. It's a composition of a product of non-trivial functions themselves. Oh, good night. This seems like it's going to be a hard. We're going to have to use the chain rule, and then the inside of which we'll use the product rule, and then I'm going to have to remember the exponential rule, and oh my god, it looks like a nightmare. Okay. It is not a nightmare. The very important thing to keep in mind is that because we're taking a partial with respect to y remains a variable. All the other variables are to be understood as constants. So x, constant. That means e to the x is a constant. X is constant, therefore x squared is constant. Z is constant, therefore e to the z is constant. Therefore this product is constant. Therefore that cotangent is a great big, ugly to be fair, but constant. And we treat the constants as if they're constants. So this is actually a really easy, what I have here is the derivative with respect to y of a constant times y squared. And there's just nothing to it, right? The y partial of y squared is 2y. And the constants just come along for the ride as constants do. Like they're k or something, just some constant of 6. Everybody cool? Everybody happy with that? Yeah.
Question about like notation. So can I just pull these out, like?
Yeah. They're just like they're a k. Yeah, you can pull them outside of the derivative. Totally fine. Yep. Absolutely. Everybody good? So, again, it looked like it was going to be super hard, and it ends up being, in fact, I would call that one pretty super easy, right? Yes?
So why would you actually have to, why would you have
Great question. That is one of the next questions that we're going to get to. Yeah, absolutely. That I owe y'all an explanation on that, and I'm coming up to it. Yeah. Okay. So just for the quick moment, I want to focus on how easy they are to compute. Here's another example. This looks like a scary one. Have y'all ever seen logarithmic differentiation? It's another one of these topics that's useful in single variable, sort of Calc 1, but apparently somebody just decided 15 years ago or something that, we're not going to teach that anymore. It's a cool trick. You don't have to know it. I do have a short video on my YouTube channel. By the way, I can't remember if I mentioned this before. On my YouTube channel, in the playlist called Miscellaneous Topics, I've got like 10 or 12 recordings in there of neat stuff that really, ideally, every Math219 student should know in some abstract, hypothetical, ideal world sort of situation. A lot of students come into this class maybe not really knowing how to do trig substitutions, for example. So I've got one on trig substitutions. A lot of students come in not knowing logarithmic differentiation. So I've got one there on logarithmic differentiation. So anyway, I encourage you to take a look at those. That said, the big idea of logarithmic differentiation is that when you have a function to the power of another function, if it was a constant to the power of a function, you could use the exponential rule. If it was a function to the power of a constant, then you could use the power rule. But when it's a function to the power of a function, you've got a nasty problem on your hands, and neither one of those rules applies, not even a little bit, at least not immediately. So logarithmic differentiation helps you get around that. Neat trick. However, in this case, keep in mind, we're taking a partial with respect to x. That means x is the variable. So this is some function of x, and all the other variables are constant. So y is a constant. Therefore, y squared is a constant. And therefore, this doesn't require logarithmic differentiation at all. I have a function to the power of a constant. Power rule. That's all there is. This is just a power rule problem. And that constant, as in the power rule, does like that. You multiply out front by the constant, you subtract 1 from that constant exponent, the function remains where it is, and then by the chain rule you multiply by the derivative of that base. So, pretty straightforward. Okay. And then likewise here, this one looks pretty similar, what appears to be a function to the power of what appears to be a function. This time, though, z being the variable, x and y not being z, x and y are constants. That means that the base, this whole base, that looks like a function is not, it's just a constant. And so here we use the exponential rule. And make sure, by the way, I hope it goes without saying, well, it is in fact written on the content syllabus. I'm going to assume proficiency with the prerequisite trail. So I'm going to assume you're good with all single variable calculus rules. Yeah.
So even these functions that we've found using partial differentiation.
Yeah.
Do we so we just substitute an xyz coordinate to get the derivative of the function in that direction? So say for
what you're effectively asking is, how do I interpret this geometrically? Yeah. And that's the same as the question she asked. So two instances of a great question, and that's going to be the very next thing we're going to do. But yeah, let's think it through carefully. Yeah. The short version is, you're kind of right. But let's make sure we study it carefully. Good. Okay, so what are the geometric interpretations? And I'm going to remind y'all of something we talked about last time. It depends very much on what kind of picture you're looking at. So you remember one of my things that I dwelled on last time was, you gotta be careful. Wait a minute, am I looking at a graph or am I looking at a level set? Because the calculus of graphs is totally different from the calculus of level sets. So this question says, hey, what does calculus look like? Right? What are the geometric interpretations of this calculus construction called partial derivative? It's going to have one answer if you're looking at a graph. It's going to have a totally different answer if you're looking at a level set. Right? So I'll remind you again, you have to have clear partitions in your mind. When you're thinking about the calculus of level sets, keep those interpretations only in the context of if you're looking at level sets. When you're looking at a graph, totally different. You're going to get totally different geometric interpretations. So you got to keep these ideas separate in your mind. So we are going to start here by looking at a graph. And you'll notice already this equation I wrote down here. That's the graph, because we're setting the function equal to a new variable. It's one of our takes on what a graph is. So here I'm looking at a graph of this function of two variables. When you're looking at a graph of a function of two variables, the inputs, typically the horizontal axes like this, and then of course the output being the new variable is, typically we would draw that upward. It doesn't have to be, but typically we would draw it upward. Okay, so in this context, now suppose that I want to take a partial derivative with respect to y. By the way, where are we on this surface? It says right here that we're looking at the point A, comma B. Keep in mind those are values of x and y. So A, comma B tells me where we are in the xy plane. But of course, I'm looking at the corresponding point on the graph. Right, so what we're going to do, technically we're here at the point A, comma B, but the geometric interpretation we're going to make is going to be a geometric interpretation based on what the graph looks like up here above that point. Okay. All right. So let's do it. Good news. This two-step process for how we compute partials, we already have perfectly satisfactory geometric interpretations of these two steps. What does it look like when you set variables equal to a constant? We're going to just draw a picture of what that looks like, and it's just a matter of literally looking at just designating those variables as constant, and it's kind of going to give us a plane. And then, what does it look like when you take a regular old derivative of a resulting graph of a single variable function? Well, we know that too. That's a slope. Right? So here we go. Let's do it. If I'm taking the partial with respect to y, that means x is to be understood to be a constant. We're going to view x as being a constant. What does that look like if I set x equal to a constant? Well, x, setting that equal to a constant means we're looking in a plane like that. Now, keeping in mind that our original surface, our original graph, was something like this. The cross section then, said differently, the part of the original graph that's relevant to this, presumption that we're setting x equal to this constant value a, is just this cross-section curve. That's the cross-section. Is that cool? Next step. Oh, and a little quick geometric observation. X is a constant, but notice that means that I'm allowed to move in the y direction. And so it's really easy to get these backwards. It's really easy to whoopsie and say, oh, well, we're doing a y partial, so we'll set y equal to a constant. It's surprisingly easy to sort of mess that up. So do think carefully. If you're taking a y partial, then x is what gets set to be constant. which has the plane perpendicular to the x-axis and parallel to the y-axis. Again, easy to mess that up. Make sure to think that through. Okay. Notice this resulting curve, and by the way, let me get rid of all the rest of this stuff. This curve gives me now z being height as a function of y, effectively. I mean, x is constant, not allowed to move. So effectively, I have height as a function of horizontal, z is a function of y. That's literally the graph of my new single variable function. And how do we take derivatives? Good old-fashioned single variable derivatives. When you have a graph of a single variable function, well, the derivative with respect to y is just slope of the tangent line, as usual. Excuse me. So we get this familiar interpretation right here. The partial with respect to y is the slope of the tangent line. That, to be a little bit more careful, slope of the tangent line to the graph of the function. Got to be a little bit more careful because we're talking about the partial with respect to y. We're talking about the slope in the cross section that points in the y direction. So whatever you're taking the partial with respect to, you're looking effectively at a cross section in that direction. And so you're looking at the tangent line that sort of points in that direction. Does that answer your question?
Yeah.
Yeah. Okay. Are you happy? Is that? Yeah. So this is the geometric interpretation of partial derivative. With respect to y, now here's what I'm going to leave as an exercise for y'all to think through. You don't have to turn this in, not exercise in that sense, but a really good practice problem. Think it through for yourself. If you were to take the partial with respect to x, this partial, still a slope, still a tangent line of the graph, this time in the x direction. Now, again, this is probably what you would have guessed, probably what you would presume based on the pattern or something, but it's a fabulous exercise to think it through. Draw this picture. Well, draw the analog of this picture now with x being the variable, therefore with y being treated as a constant. Think through what that would look like. It's going to be a different kind of a cross section. You're going to have a different cross section curve, blah, 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 and you will interpret this result. So again, think it through. I think it's a good exercise, and this is what the answer is. Everybody okay with that? All right. Okay. Now, can't emphasize enough. I can erase. Cannot emphasize enough. Depends on what kind of picture you're looking at, right? So yeah, this is what a partial derivative looks like if you're looking at a graph. We will not always be looking at graphs. You can't say slope of a tangent line if you're not looking at a graph. So we have to now entertain totally different question. How would I interpret partial derivative? Again, just regular old partial derivative. How do I make sense out of that if I'm looking at this other kind of picture, this literal picture? And first, easy observation, I can't talk about a slope of a tangent line. There's nothing to be tangent to, right? There's no shape to look at. All right, so how should you think about partial derivative then in this context? And let me just remind y'all, derivatives in general, we understand this is an old, this is a version, this is a tweak of an old formula from single variable calculus, that derivatives are what you multiply by input differentials to get output differentials. You might have seen the appeal of, you sort of cancel the dy's. Kind of, sort of. But anyway, old fact from single variable calculus, single variable derivatives are the factor you multiply by input differentials to get output differentials? Well, partial derivatives are single variable derivatives in the sense that, they're the single variable derivatives of what's left once you set the other variables equal to a constant. So if y is my variable, y is the only thing that's allowed to change. That means x and z are now fixed. X can't change, z can't change. Oh, I missed the thing there. Here, let me cheat and do it like this. So x is not allowed to change from that value a, z is not allowed to change from that value c, and that means that I'm moving in the y direction. And with that understanding that this partial derivative addresses the question of what happens as I move only in the y direction, the partial derivative is the relationship between input change, input differential. I actually want to use green for this, and output differential. So the partial derivative is what you multiply by the input change to get the output change. Approximation. Not a slope. Right? Again, can't be a slope. There is a line. Can't be a line because there is no shape to be a tangent line of. So totally different interpretation. When you're looking at this literal picture, there's something less satisfying about this point of view, but this is the point of view to take if you want to have an intuition for partial derivatives in the context of these literal pictures. Yeah?
You've used the D symbol and they're not interchangeable.
Yeah, they're not interchangeable. No, I've done this the right way. So the idea of this, what I have in orange here, this partial derivative, right? We've got this thing called f. F is a function of several variables. I can't take a single variable derivative of a function that has multiple derivatives. So I have to say partial derivative, and that sort of encodes the fact that, hey, we are making this weird choice to pretend that some of these variables are constants. Right? This dy right here is not at all connected to this notation. Dy is just a differential. It's not a derivative at all. Dy just says, look, y might change a little bit. And dy says, how much did y change? That's all it is. It makes no assumptions about what's happening in any other direction. Right? This does, right? But dy just says, look, if y changes by some amount, that's all. And then likewise, df. This is, again, called a differential. This is our linear estimate of how much the output changes. Now, technically, the actual change in f is always a little different, right? The derivatives just give you approximations. But the linear estimate of that change is what we call the output differential. Yeah. So yeah, I know it looks a little weird. It looks like a hate no fair kind of thing, but it's actually fun. Anybody else? Everybody happy? All right. That's our sort of second point of view. What about if we're looking at a level set? Now, again, if you have a function of several variables, level set. Oh, I'm sorry. Yeah.
So this previous page is saying that to find the partial differential for this this picture, you're doing out for change divided by.
Well, I hear where you're coming from, and it is a constant frustration for me, I'll say, that this notation is written the way it is, because it looks like a fraction. And very importantly, it's not really a fraction. Now, we write it like a fraction because in many ways it sort of behaves like a fraction, We're going to find later on, in fact, that importantly, in certain ways, it doesn't behave like a fraction, but it looks like a fraction, and as such, people are constantly sort of trying to figure out, wait a minute, what does partial f mean by itself? The answer is it doesn't mean anything by itself. Don't think of this as a fraction. It's not a fraction. This is not a well-defined thing divided by a different well-defined thing. It just isn't. Think of this as a single notation that represents this one quantity called the partial derivative that we computed, like we described before. Does that make sense?
I guess what I mean is,
okay.
If you move the dy to the other side, like moving df over dy equals...
Yeah, that's, we get into, true. But when you do that, let me write down what I think I understand. You're talking about taking this and bringing it over here, right? And effectively saying df over dy, like that, right? You can do that, but now this thing is a fraction. And this thing on the left now is not a derivative. Yeah, this is a independently defined thing called df that we've chosen to divide by this independently defined thing called dy. And I can't call it a derivative because if it were a derivative, the use of d's would mean it would have to be a single variable function, and f isn't. So yeah, it's just not a derivative in that sense. Yeah, and I know isn't it awkward, right? And I blame the notation. If I had control over all of mathematical culture, which I don't, right? Not even close. I want to make a change of some. I don't know how exactly, but I definitely want to make a change of some sort to this unfortunate notation. And all I can do is just kind of apologize for it, I guess. Yeah. Okay. Level sets. Now again, different context. We've talked about the calculus of graphs. Let me rewind to it. Here is calculus of graphs. Some of the calculus of graphs, that is. Partial derivatives are kind of a calculus. We're interpreting them in the context of graphs. So this is calculus of graphs. This is not. This is what you might call, I guess, part of the calculus of this literal picture. Now, we're going to talk about a third thing. This is neither of the above. So in the third partition in your mind, we're going to talk a little bit now about the calculus of level sets. It's going to be totally different. You're going to notice, for example, very tempting to look at something like that and say partial derivative. Partial derivatives are slopes, and so maybe is the partial derivative the slope of the curve? And no, not even close. Big X. Because that's not a graph. Right? This is understood to be a level set of f, not a graph of f. So I can't use the calculus of graphs. I don't want to hit that point too hard, but I don't want to hit it not hard enough either. So anyway. Okay, so we got to figure out how to make sense out of this. What would I interpret from partial of f with respect to x, given that this is a level set? And I'm going to make the appeal back to thinking about these level sets as being contour lines. Right? So imagine you're out hiking, and what would happen if you were climbing like so? And I'll just make the observation that, let's see, let me zoom in a little bit here, if I can. Here we go. Hiking in the x direction, between there and there, I just gained 200 feet of altitude over a very short distance. That would be very steep. And that suggests a very high value of the partial derivative. In other words, if I were looking at a graph of this, the graph would be steep. Steep graph means a large slope, means a large value of the partial derivative. Okay, so this arguably is why The x partial is large. And now by contrast, if I go in the y direction, as I'm going in the y direction, I can still gain that same 200 feet of altitude, but I gain that 200 feet of altitude over a much greater distance. Now again, think about the hiking. Well, that's more my speed of hike these days, right? It's a nice, gentle climb. And less steep of a graph, and therefore a lower partial derivative as I go in that y direction. And so as I have, I'm off the page, here we go. As I have here, in the same way that the x partial is large because of how quickly I gain altitude in that direction, the y partial is small because of how slowly I gain altitude as I go in that direction. Everybody good? It's a little counterintuitive. You see a shorter arrow here. Shorter arrow here because they were interpreted in this totally different context of level sets. Shorter means bigger. And longer means smaller. Something to keep in mind. Okay, moving along. So linear approximations, y'all remember this stuff here, I presume. Well, in particular, I'm sure you remember this formula for what's called the linear approximation of a single variable function, in particular a differentiable single variable function. Everybody ring a bell, right? Flashbacks? Okay, cool. There's different takes on where this comes from and how do we define it and what role does it play, blah, blah. I'm going to take a certain point of view on this that I think is most helpful to where we're at as follows. What we're going to call the linear approximation is, by the way, we're going to assume that it exists. That's a subtle point of formality that I'm going to have to come back and talk about in a minute. Well, tomorrow. But we'll come back and talk about that. But assuming it exists, the linear approximation is the unique degree 1 polynomial that has the same value as f at the point A and that has the same first derivative as f at the point A. And make sure you're good with seeing why these two requirements, 1 and 2 down here, why are these satisfied by this equation? Now it's just a plug and chug, but for part 1 here, you've got to plug in x equals a, plug that into this formula for L, and confirm that what you get is f of a. That's easy plugging in, but take the 3 seconds to figure that, to make sure you're comfortable with that. The taking the derivative part's a little trickier, because you got to keep in mind, it's really easy to forget this. Here it is. But this is a constant. And it doesn't look like a constant because why will that not? Oh, my pencil died. All right. Oh, now this is, I don't know what's going on here. Will it let me, okay, I can write, but I can't erase. Okay, I'll leave it, whatever.
I think it's because Bray was already in the notes.
Oh, thank you. That would have driven me crazy. You're right, it is part of the note. Thank you. Oh, God. Oh, my gosh. Okay, so this I can erase. Good. Yeah, so this is a constant. It doesn't look like a constant. It says f prime. You're thinking it's a function. Functions aren't constants. But this is not f prime. This is f prime after you've evaluated at a given fixed point A. Right? So f prime of A is just some number. It's a number that came out of a function. Yeah, sure. But it's a number. It is a constant. Right? So with it, keeping in mind that that is a constant, take the derivative of both sides, plug in the value x equals a after you take the derivative. Confirm that you get f prime of a as your answer. And again, make sure you can do that, right? But fill in the little detail devils on that. Make sure you're good to go on that. Okay, so that's a flashback to single variable calculus. In multivariable, we're just going to do the exact same thing. I'm just going to say, look, I want to know what is the function that has the same value as f, and that has the same wait a second. We got a bunch of different derivatives, a bunch of different partial derivatives. I'm going to require that all of the partial derivatives of L agree with all of the partial derivatives of f. And the function that does that has this formula right here. And let me make another quick notational reference. This notation here is a variant of this notation here. The business about putting the a there, y'all are very familiar, I'm sure. If you say f prime of a, that parentheses a means, okay, evaluate at that point a. And that's all this means. When you have a vertical line with a subscript, that's just kind of an alternative way to say I want to evaluate this at a. And the reason that I write it like that, well, a couple different reasons. One is it's good for you all to be familiar with various notations that you're going to see in your futures, and this is one of them. So it's a nice opportunity for me to do that. But I also think it's a little bit weird. I don't know. I don't know if you noticed, but it's a little bit weird how I have a parentheses followed by another parentheses up here, and these parentheses are interpreted in different ways, and this means evaluate, and this means multiply, and y'all are accustomed to seeing this particular one because you've seen it a bunch of times, and so I knew it wouldn't throw you a curveball here. But I was a little concerned here it might. Right? So that's why I made the different notational choice, and so all you got to remember then is that this just says take the partial of f with respect to xn and then evaluate it at your point A. It's totally analogous to that, just with partial derivatives. And what I'll leave you with, again, a suggested exercise. Make sure that you can confirm these two properties for this function. And what you'll find is that, yep, sure enough, it works. Come talk to me in office hours if you have any trouble with it. We'll draw the line right here. Sorry, it looks like I went several minutes over. My bad. See y'all tomorrow or in office hours in 12 minutes. Have a good one.